Hi everybody, my name is Michael Edgar and welcome to the first video on ion chromatography. So this is going to be part one, which is going to cover background and sample prep. We're going to answer questions like what is the IC, what can I measure with the IC, how does it work, and how do I need to prepare my samples. So first of all, what is the IC? IC stands for ion chromatograph. It has two flow paths, one that analyzes anions, which are negatively charged molecules, and one that analyzes cations, which are positively charged molecules. The most common anions that are analyzed with the IC include fluoride, chloride, bromide, nitrite, nitrate, sulfate, and phosphate. And the most common cations that are analyzed with IC are lithium, magnesium, sodium, calcium, ammonium, and potassium. You can measure more things than just these, but these are the most common ones that you look at. Chances are a lot of you guys just want to toss your samples over to somebody who knows how to use the IC without actually understanding how it works. So I'm going to cover how to prepare my samples first because this is one of the most important parts of running the IC. The first thing you want to do is make sure that they are in the appropriate concentration range. Normally the IC measures most ions between 1 part per billion and 100 parts per million. In general, you want to go lower. Lower is better. The IC measures things lower more accurately than it does higher. In addition to that, going too high is going to overload the column. It'll give you bad results and potentially damage the IC. You might think you're saving yourself time by not diluting your samples, but when you get bad results and you have to dilute them anyways, and you just wasted a week because the IC was running with all your samples that were too high concentration, you end up losing a bunch of time. Now, even if you don't want to measure a certain ion, high concentrations of that ion can still interfere with the ions that you do want to measure. So always dilute based on the highest concentration ion that you have in your samples. The second thing that you need to do is filter them. In general, you want to use a 0.45 micron syringe filter or something smaller, and centrifuging also works, but talk to the person running the IC to make sure that it's okay. Now we'll move into a basic overview on the IC. I'm going to refer to this image a lot because it kind of just goes through the general flow path. And we'll run through each one of these parts individually. So we have our eluent, which goes through a degasser. We have the pumps that push eluent and all of the flow through the system. We have an injector, a guard column and analytical column, a suppressor, and a conductivity detector. First, let's talk about the eluent. So what is eluent? Eluent is the mobile phase. This is the liquid that flows through the system as it's being pushed by the pumps. Some ICs require that you make your own eluent, while some require nanopure water that flows through an EGC. EGC means eluent generator cartridge, which uses an electrolytic chamber to turn very concentrated eluent into a more diluted eluent for your IC, based on a current that you apply to it. That's what this picture is on the right. This is an EGC. Anion columns use a base, which is usually potassium hydroxide, and cation columns use an acid eluent, which is usually methane sulfonic acid. You may hear the term carb-bicarb systems, and that's because carbonate and bicarbonate eluents are also very common with IC. So back to this image, we see that our eluent is pushed through the system by the pumps. It goes through a degassing device, which removes gas because we don't want any air bubbles getting into our system, and then it makes its way to the columns. But somewhere in here, we need to get our sample into the column, so let's talk about how that works. You usually have an injector and an autosampler. The autosampler is a tray and needle system that draws your sample into the sample loop. Now, the sample loop is a coil of tubing that holds your sample until it is ready to be injected into the column. The injector is a multi-port device that'll change positions when your sample is ready to be injected into the column. Normally, this injector is in a position where eluent can flow through it and straight into the column, but as soon as your sample is in the sample loop and ready to be injected, this port will open up for your sample to go into the column, inject the sample, and then it'll go right back to eluent so that eluent can continue flowing through the system. So now that your sample has been drawn into the autosampler and injected by the injector, it'll pass through a guard column, which takes out any nasty things you don't want, like hydrophobic organics or heavy metals, and then the sample goes into the analytical column. The analytical column is the heart of ion chromatography. It's made up of either anion exchange or cation exchange resin. This causes ions to adsorb to the resin, and then eluent pushes off the ions off of the resin. So ions with a higher affinity will take longer to come out. And what this affinity means is how stuck to the resin is this ion. And this has to do with the ion's charge, its size, its electronegativity, and some other things. But basically, the harder something is stuck to that resin, the longer it's going to take to come out. And this allows us to separate out these ions so that the conductivity can measure each ion individually. Based on the time that it took for the ion to come off, we can tell which ion was which. Over time, we're generally going to increase eluent concentrations to elute ions, and this term elute basically means to push them off of the column. So now your sample has passed through the analytical column and your ions are starting to elute. They need to make their way to the conductivity detector to be measured, but there's one more very important component before we get there. This is the suppressor. So without a suppressor, your background conductivity would be huge from your eluent. We're using acid and base concentrations in our eluent, and that has a lot of conductivity, so we need to suppress that first. The suppressor uses various electrolytic reactions and semi-permeable membranes to convert your eluent into water and waste. The example on the right here shows a sample leaving an anion exchange analytical column in a potassium hydroxide eluent. The electrolytic reactions taking place on the sides here convert your base into water and your cations into waste. It's not super important to understand all of these reactions, but it's important to understand that the suppressor is essential to getting good conductivity measurements. Setting your suppressor's current too high can result in seeing no peaks at all, and setting your suppressor's current too low can result in ridiculous looking massive peaks and a ton of background noise. In the end, the only thing that passes through your suppressor is nanopure water and your separated ions, so your conductivity detector can work efficiently. The conductivity detector measures conductivity as ions pass through the column, and this makes peaks. As an ion passes through it, the conductivity increases, and it can move on to the next ion. The area underneath these peaks correspond to the concentration of that ion, and this is based on your calibration curve, which we'll talk about how to make in the next video. You use these chromatograms to get your result. So your area corresponds to a concentration, and the Chromeleon software will automatically make an Excel file that you can use to analyze your data. So that's all for now. Thanks for listening, and be sure to check out the next parts to these videos to learn how to set up and run the IC. Thanks.